One of the big projects that I'm very excited about that's at an early stage is a project to try to understand ALS. This is the disease caused Lou Gehrig's disease, and many of you are probably familiar about it from the Ice Bucket Challenge. And so ALS is a neurodegenerative disease which strikes most people seemingly at random. Most people do not have a family history of the disease. And we understand very little as a field as what's wrong in these patients that led to the disease. And so we're trying to find the molecular cause or more likely causes of the disease in these patients. And to do that, we've teamed up with scientists across the country in an extremely large project that starts in the clinic, where we're gathering about 1,000 patients. And these patients have agreed to not only give us information about their disease, but also to give us cells that we're going to take into the laboratory and using something called induced pluripotent stem cell technology, turn them, the skin cells or the blood cells, turn those into the neurons that suffer in the disease. And those neurons will then be analyzed in our lab and other laboratories at the molecular level to find changes in the proteins, changes in the genes, changes in what's called the epigenome, which is the signal that tells us what part of the genome is getting turned on and off in different cells. So that'll produce a vast amount of data, small molecules as well. And we're also collecting data on the patient's clinical parameters. And we're also going to outfit them with wearable devices to find out how their disease is progressing. If they're losing mobility, at what rate are they losing mobility, what rate are they losing their ability to breathe well. And so once we have all of that data, then the question is, can we use that to break the disease apart into different subtypes? It may be, and it seems very likely, that ALS is not one disease, but there might be multiple causes. And so by gathering all this data, the first thing we can do is try to find groups of patients. These patients show one kind of disease symptom, and these groups show another. Having the richness of the data, both from the clinic and from the cells, allows us to then say, what is the molecular basis for these different subtypes? And for that, then we then hope to build basically a map of what's going on in the cell and see within that map where the proteins, the genes, the small molecules are that are really causing the disease changes. And from that, then we can go back into the laboratory and see, well, what happens when we take drugs that target those molecules? Does it make the disease better? Does it make it worse? The maps that we use to understand disease states begin with a vast literature that contains tens of thousands of interactions between molecules in the cell. In fact, when you bring in both protein interactions with each other and proteins that interact with small molecules, it's actually more than 1 million known interactions. Those are all literature verified. Some of them are extremely high confidence and some are lower confidence. And we can even add on top of that predictions from the computer of molecules that interact with each other. And this gives us a vast network. You can think of it like the internet or perhaps a street map. It doesn't tell us what's actually the traffic on that internet or on those streets, but it gives us the grid of the city. So now when we want to go searching for which molecules are important, we start by looking for neighborhoods that are important. Where's the activity in the city? And so we look for the molecules, the proteins that are changing, and we try to zoom in on the neighborhood in this map where all the changes are occurring. And this approach of taking a very data-driven way, where we start off with a map and then we let the data tell us where in the map to go, can be contrasted with two other approaches that are useful but limited. So one approach is to focus in on individual molecules, and I was trained in biology, and that was historically the way biology was understood. You focus on a molecule that you believe to be important, and you learn a little bit about its neighborhood. But now we're really zooming out. We're going not just in that individual molecule and what's near it, but farther and farther afield to get a sense of the entire complex set of pathways that are altered in the disease state. The other thing one can do is look for previously reported pathways. People know that something's involved in how glucose, how sugar gets used in the cell, or how certain fatty acids get used in the cell. And that has quite a lot of value as well, but it's limited because our knowledge of these things is quite limited. And so in controlled experiments, when we do something to a cell where we think we know what to expect, we usually find that the data tell us a lot more is changing than we expected. And so these more unbiased methods that rely on this map of interactions that is partly computer-driven, partly driven by high-throughput experiments that measure in an unbiased way the interactions among molecules, and then also partly derived from literature, allows us to go far beyond what we can get by just looking at the annotated pathways, the things that people, the references that people already know.